Quiet down. All right, so I just want to very briefly go over the exam. Just some of the statistics. So the average, kind of typical, 50, mid-50s. A pretty big spread, right? So the high score was a 95. There was actually 6 grades in the 90. I was pretty happy with how many. Usually there's not too many, at least during the first exam. So again, I sort of broke this down a little bit in terms of what the grades might mean, right? But really at the end of the day, what's going to happen is there's no sort of formal curve, right? What happens is at the end, I'm sort of going to look through the breakdown. I'm going to look at how, I'm probably going to look through a bunch of finals and sort of gauge what those numbers mean in terms of a standard grade. But again, the average is about a 56. Many people have come to me already and said, if I have 40, can I get a B in the class and things like that? Or if I got a 60, can I get an A? And, it's anything's possible. It's only a certain percent. The challenge, though, is, right, if you don't have, if you didn't do too well, then that suggests that your knowledge base might be lacking in certain areas. And so generally what happens is on the lower end, it's very difficult to catch up, right? So nothing's impossible, right? But if you're on the lower end, you really have to work a lot harder than a lot of other people at this point to sort of catch up and move forward. And so I thought the best way to just sort of illustrate that is some of the statistics, right, in terms of the last time I taught the course. Now I should probably say this with a grain of salt, right, because that semester was a little bit of an anomaly because of Sandy and all the complications that came with that. But at least you guys can see what are the scores that people got on previous exams and sort of what was the distribution of the grades at the end of the semester. And that'll at least give you an idea. One of the things I think is worth noticing, though, is that it's pretty spread out, right? Especially in certain areas. Like, you look at the 80s, right? And again, an 80 is a very strong grade. Like, it's certainly an A. But what happens is, certain people might get too overly confident and start slacking off. Other people might sort of step up and really work. And so, in fact, in the 80s, almost all the A pluses from last semester came from people that had 80s, and there actually is a single A plus of people that got the 90s, right? So again, what does this mean? I don't know. I'm just throwing the numbers up there so you guys can see it, and so that you can, because again, you guys come and ask me, well, can I do this? Can I get this grade if I have this grade? And I don't know. It depends on what you do, but this at least gives you statistics of what happened previously in a previous semester, so you can actually see really what happened. And again, the grade distribution wasn't entirely different in terms of the average and so forth. The average on the numbers that I have here is a 60, but this, in fact, was the data that I was able to get my hands on this morning, and it doesn't include the students that dropped the course. So there was about probably 20 students that dropped the course last semester. So anyway, again, here it is. If I would, there's over 200, I think there's 220 of you or so. So it's going to be very difficult for me to meet with everybody like one-on-one, but certainly, or give too much time, but if you have to come by and ask a question, hopefully this will answer a lot of your questions. But certainly come and talk to me if you have questions, and I will do my best to sort of answer them, okay? So again, this is actually on my course website, right? So it'll be, right? I actually just have it next to where my lectures normally are, so. So it's just going to be, I just have it sort of where I would normally have the PowerPoints, just right next to once I put up this class from today, it'll be right next to that. All right, so you can sort of take a look at those statistics and sort of keep them in mind as you're sort of deciding, if you want to drop the class or if you want to sort of know where you stand. I think that sort of data from last semester is really probably the best. It's really the best answer that I can give you guys in terms of just sort of realizing that have people in the past gotten A's and getting certain ranges, but also sort of noticing that even people that got very good scores still sort of fell off. So again, my office hours today will follow this class, and again, they usually go till about 2 o'clock. So, all right. Okay, so within that sort of question of how, in terms of knowledge base being off, I hopefully made the point over and over and over again that, I teach the course very mechanistic standpoint, and so it's very important that you're able to do mechanisms. And I was actually pretty pleased with how you guys did on that final question by and large. I really think that, that many of you guys are really putting in the work to understand mechanisms, and even if you see something you haven't seen before, you're still making some rational arguments to get there. So I was actually pretty happy. I graded all those mechanism questions, and I was pretty happy. So hopefully that should mean that we'll do okay, right? So again, as we move forward in the semester, and really over the next probably 5 weeks, we're just going to be learning reactions and lots of reactions, and each of these reactions is going to have a mechanism to it. And so what you should be paying attention to is, again, focus on the mechanisms that I draw. And what I would sort of challenge you to do is when I put a mechanism up there, don't just sit passively and start writing what I'm writing. Actually think actively about what I'm planning on writing, and even try to sort of beat me to the punch and see, is the arrow that I'm planning on drawing what Professor Murelli's planning on drawing? And if it's not, then ask yourself, well, what's wrong with it? Is my arrow going in the wrong direction? Is there something wrong with it? So really be proactive as I'm going through the mechanisms, and really try to, nail this down. Again, because again, we're going to be studying a lot of different mechanisms, and this can sort of both reinforce your knowledge of mechanisms as well as learn these different reactions. Okay, so for the next 2 classes, actually the next 3 classes, what we're going to be talking about is the reactions of molecules that have p orbitals, okay? And so today's class is going to focus on alkenes, and next class will focus probably on alkenes as well. Maybe we'll get into a little bit of carbonyl chemistry. But from a mechanistic standpoint, and sort of thinking about reactivity, the one new thing that we're learning here is going to be the sort of first step in many of these reactions. It's sort of starting to get comfortable with seeing alkenes behave as nucleophiles, right? And in some cases, we'll talk about them behaving, or pi systems behaving as electrophiles as well. And so, as you see in a case of an alkene, right, we don't have any lone pairs, right, like we typically would in, say, hydroxide, like a base, or standard bases that we've seen, or standard nucleophiles that we've seen. But as it turns out, the pi system can actually behave in many ways as a nucleophile. So this is going to be, by and large, the bulk of the alkene chemistry that we're going to see is going to be initiated by alkenes behaving as nucleophiles. Okay? And so one of the ways that you could think about this, right, is perhaps to draw a resonance form. And again, this isn't going to be a likely resonance form, but it will be a resonance form that might help explain the reactivity of this compound. Right? And so while the alkene itself, right, might not seem to have a lone pair in it, if you draw the resonance forms, now you start to see that lone pair, right? And it's in fact through this resonance form that, at least at the beginning, as you're trying to get comfortable thinking about alkenes, you may want to think about this intermediate being this sort of nucleophile, right? And so this is what we could use to react. Now notice that there's symmetry to this as well, and we'll get to that, but as I've drawn it, it's symmetric, but I'll just to sort of be complete, I'll sort of draw the other way as well, right? We could have that arrow going the other way, right? In which case we have a carbocation on this side and the anion on this side, okay? So this we'll get into a little bit later as we're talking about the reaction. There's certain regioselectivity that occurs that sort of deals with the fact that you could imagine either of these cases. And so, again, if you start to think about an intermediate like this, now we can start to do our standard substitution reaction. We can start to think about our standard acid-base reaction. And so, if you might imagine, if you took a molecule like an alkene and you treated it with an acid in the presence of, say, water, right? So that could be sulfuric acid. I'm just going to sort of write H plus to simplify things, right? The first step would be, right, that we would take this lone pair and we're going to react it with a proton, right? And what that's going to lead to, right, is a carbon-hydrogen bond, right? And again, as you sort of map the electrons, right, the electrons that I sort of drew in blue there that reflect the 2 electrons that are in that pi system are now making that bond, and I should have a carbocation. Yes?
Can you draw straight from the...
Yeah, I'll get to that. I just want to go through first, because I think sometimes alkene chemistry, you know, just every time you add a dimension, it's just something else that people can slip down on. So I just want to sort of illustrate it in terms of what we've learned first, right? Resonance forms, right? This exists, this is how it might exist, but if we're talking about the reaction, perhaps this is a better way, at least at first, to rationalize how the chemistry happens, specifically if you struggle with the direct way. But we'll get into the direct way. Hopefully, most of you will get comfortable drawing it directly, but I'll get to that in a moment. Okay, so in this reaction, right, we'll have a carbocation, right? And now let's just try and predict what would happen, right? We've got acid and we've got water. What might happen in this reaction? What do you think? Joyce, what do you think? Right, so this oxygen now we're getting back to standard. What type of reaction would that kind of be similar to? An SN1 reaction, right? So you've got a carbocation, you've got a nucleophile. It's not an overly strong nucleophile, but there's a carbocation. And so the fact that this oxygen has lone pairs, right? We don't show them, but they're there. I'll make some of them in red and some of them in the standard color there. And so what's going to happen is this is going to attack the carbocation, right? The net result of that will be that we will now have an oxygen-carbon bond, right? A new oxygen-carbon bond. Focus on its colors. And again, for some of you actually who've asked me or have struggled with electrons, you know, when I was at Boston College, I used to see students, I used to sit in TA and I would hear students in the back with like clicker pens with different colors, and they color coordinate everything. And it seemed to help them. So again, I suggested that to some people. I'll suggest it to the class in general if I haven't already. But again, it's just a way to sort of keep track of all of your electrons. Because again, chemistry is, you know, we don't really, when we're talking about chemistry, we're generally talking about the electrons, right? And the sort of movement of these electrons. Okay, so conservation of charge here. Where am I missing a charge? Exactly, right? So my oxygens have a positive charge on it. And again, so at this point, several things can happen. But in this case, what we're going to do is we're going to deprotonate one of those hydrogens, right, to basically help the positive charge on the oxygen. So many things could deprotonate it. This is one of the challenges as we start getting into acid chemistry. It turns out that this is a catalytic process. So you could imagine whatever the acid is, if it's sulfuric acid, the sulfonate could go back and react with it. You can imagine the alkene itself going and deprotonating that and getting back into it. What I'll do is I'll just use water now because we've got a lot of water around. Okay, and that water will just go and take off that proton. Right, and that's going to put those electrons onto that oxygen. And the net result will be that we have just added water across an alkene, right? And so if we sort of color coordinate, okay, does everybody see that, right? So the product of that would be H3O+, and again, the H3O+ could serve as an acid here. So oftentimes, you just need a catalytic amount of acid, and you can just sort of run this reaction, okay? So again, this is sort of the very first reaction of alkenes we're going to see, and what we're going to notice is that many of the reactions of alkenes are going to follow a very similar trend. The alkene is going to serve as a nucleophile. It's going to react with something, either an acid or an electrophile, as we'll see. And then usually what will happen is then another nucleophile of some type will come in and displace the other thing. So you'll often get something at one carbon, right, and then something at the other carbon. And again, if you think through the mechanism, you should be able to reason these. And again, as I was sort of stating a couple weeks ago, the goal in terms of understanding the mechanisms should be, when we're learning these reactions, to try to compartmentalize these reactions, right? We're probably going to learn a good 60 reactions, and you don't want it to feel like 60 reactions. You want it to feel like maybe 15 reactions. And so as we're going to see, many of the reactions within alkene chemistry are virtually the same or very similar when we consider mechanisms. Yes?
If the H plus wasn't there, would the negative charge made by the alkene attack, would there be two OHs?
So yeah, so would there be two OHs?
In the final product?
No. You will learn a reaction that does that, but not this one. Again, water and an alkene aren't really going to do anything. You need the acid to initiate it. You need to sort of generate this more reactive intermediate. And you need actually a fairly strong acid to do this. So
why wouldn't the lone pairs made by the double bond then at least it should have one OH because of the positive charge.
It does.
You know what I'm saying? If there was no H plus.
If there was no H plus, then the H plus is an acid. The reaction won't go. Water is not reactive enough. You could formally draw a mechanism, right, where the water would be the acid, but water's not quite acidic enough, right? That would be in the, in terms of that level, right? Sort of in terms of H2O to OHO minus. That's not going to Joyce.
What if it's not? The H3O plus deprotonate with H, like how it keep on going?
That's the point, right? So the point that Joyce was asking is, if you've got, right, so that the proton is actually catalytic. We really haven't discussed this. I don't want to overcomplicate it more than it is. But yes, you could in fact draw a circular, come to my office hours, I'll show you, you come to my office hours, but I can show you how you sort of continue to regenerate. You could in fact continue to regenerate that H+. And so in essence, if you really wanted to run this reaction, if you have one equivalent of water and one equivalent of alkene, you don't need one equivalent of acid to get that whole process to go. But that complicates it beyond what I really want to focus on right now. But again, you can come and talk to me about that if you want. Okay, so this is the sort of first alkene reaction. Now, what I'm going to show you next, so what we're going to do in large is we're not going to start going through this intermediate, but at least in first, if it's going to help you to see what's happening, you can go through this intermediate to help you think about it at first. But as was just stated earlier, can I just draw this arrow directly to the proton? Yes, and that's what I'm going to start doing from now on. And again, it's just going to save board space, but again, going through this intermediate might be helpful at first to keep track of where everything is. Okay, so now imagine that we're running this exact same reaction, and what I showed you, right, was a symmetric alkene, right? So I could have gone to the other carbon as well, and it would have led to the same product, right? So there's that sort of symmetry to the molecule, but chemistry is obviously not always that neat. And if we have a situation where we have, say, an alkene that's not symmetric, right, where on this side we have two methyl groups, and on this side we have two protons, we're going to get one of two products, right? We're going to add water across this, right? And we're going to get one of two products. Either we're going to get this product here, right? So that would be one possibility. The other possibility would be that we switch the sides of it. What's that? Yeah, so that we'll have the hydrogen over on this side, and we'll have the OH over on this side. Okay? So now there's going to be a rule that you're going to learn, and many of you will try to memorize this rule, and it'll be called Markovnikov addition. But again, from a mechanistic standpoint, based upon what we've learned so far, we should be able to rationalize in this reaction which one of these two products it's going to go to. Okay, so I want to ask you guys to think about, just for a couple, 20 seconds or so, draw the two products of acid with this alkene, and think about those two and ask yourselves which of those two is going to be more stable. Okay, so just everybody draw that out right now. The two carbocations that you can generate by treating this with acid. Yeah, the carbocation intermediate. So I want you to react this with the acid, and two possible products, so two possible intermediates can form when you react that alkene with the acid. There are going to be two carbocation intermediates. Okay, so I'm going to go ahead and draw it. Let's see if you guys have it. Right, so just check to make sure that you're drawing the same thing that I am. One possibility would be to protonate this carbon, right, for the protons to end up on this carbon, in which case a carbocation would end up over here, right? See that? If I protonate this carbon, I'm going to take these electrons that are in here, I'm going to use them to make a bond, and the effect of that is that I'm going to be taking these electrons away from that carbon, right? So I'm going to be taking those electrons away from that carbon. leading to a carbocation there. And again, the fate of these two electrons are that now they're going to be in a bond with that carbon-hydrogen bond. So that's one possibility, right? The other possibility would be to go the other way, right? That we're going to take those electrons, they're going to stay on this carbon, they're going to move away from that carbon, and we're going to form a bond on that carbon-hydrogen bond. I'll just draw the protons here, right? And so we'll have now a carbocation in this carbon. All right. So now the question is, which of these two carbocations is more likely to form? How many people think the top one? How many people think the bottom one? Right. Why? Tertiary, right? So the more substitution that you have on a carbocation, or the more sort of, if it's tertiary, there's sort of that hyperconjugative stability going on, right? And so it's not going to go to this carbocation, right? So we're not going to form that. Or we're not going to be as likely to form that, right? We're going to more likely form this one here, right? And so now what's going to happen? The H2O is going to add in, and which of these two are going to form? The left. Right? So the H2O, again, we can draw that in, and I'll just do 2 arrows. Right, we're going to form that in, it's going to make an oxygen-carbon bond, and then just look at the mechanism from the previous one that we drew. You're going to have to deprotonate that proton, and you're going to end up with this alcohol. Yes?
If we had a really bulky, instead of an H2O, we had like, I don't know, like a carbonyl oxide, would we not be starting to like
That's an interesting, yeah. That's a really interesting question. So the question that was asked is, if you have a really bulky carbocation, or sorry, if you have a really bulky nucleophile, right, would it have an effect? What do you guys think?
That one, you consider the anti-oxidant.
Well, elimination would go back in the reverse phase. Yeah.
It's trigonal planar, so it would be.
What's that?
Wouldn't it be trigonal planar, so it would be less likely?
Well, yeah, it would certainly be right. So that's right. So I think you're almost there, right? So what he's saying is that if you're going through a trigonal planar intermediate, right? This is a carbocation, so it's trigonal planar. There's not as much sterics to it. But what does this more closely resemble in terms of a substitution? An SN1 or an SN2? SN1, right? Because we're going through this intermediate. In an SN1 reaction, does a nucleophile matter at all?
No.
Right. So the argument would be probably not going to matter at all. Now, again, you have to sort of keep a certain element of open mind here, right? Because chemistry is not always as neat as we draw it on the board, right? So maybe it's too bulky and maybe you get some other weird elimination. Maybe it never goes and it just goes in the back direction and stuff like that. But it could still, in principle, happen. And I think at this point it's good to be thinking about those things. And the question is, yeah, maybe a bulky, maybe if it was T-butanol, it wouldn't work as well. You know? And so that's good to be thinking about. But that's just another level of complexity on top of it. But right now, let's just focus on this mechanism, but I love that you guys are thinking about this, okay? So again, so when water adds across an alkene, you guys can go ahead and memorize that, when I add water across an alkene with acid, right, it's going to go to the OH is going to go to the more substituted carbocation. Right? And so a lot of you guys will sort of think that, and you'll try to memorize that, and so forth. And then what will inevitably happen is you'll get to a compound like this. And the question will be, in this reaction, what's going to be the product that's going to form? And one of two products can form. Right? And so one of those two intermediates can form, and the question is either of those more stable than the other? No, right? Neither of those is any more stable than the other. And so this is why it's important to think about the mechanism, right? Both these are secondary carbocations, right? They're both secondary carbocations. There's no resonance stabilization in either one. This one has maybe, hyperconjugation between a carbon-carbon bond, whereas this one has a carbon-hydrogen bond. That's a very, very subtle difference, and it's not really going to matter at all. But the problem is what a lot of students will do, right, is that they will sort of memorize this Markov-Nikov addition as being, oh, the more substituted carbon. And they'll say, oh, this is the more substituted carbon. That's not really what we mean, right? And that's why I think it's important, again, a picture says 1,000 words, right? And so if you sort of understand why this is going to one or the other, you can at least look at a situation like this, and you won't get confused with how some of the words that the book uses or that myself or some of our recitation instructors will use that might be a little bit ambiguous. Okay, so again, it's all about the stability of the carbocation. The Markov-Nikov addition is talking about the product which goes through an intermediate that has a carbocation that's more stable. Yes?
Since it's going through an intermediate like that,
Mm-hmm.
and there's a potential for like an alkyl shift, like, there could be some sort of like just for more.
Yeah. So the question was just brought up about alkyl shifts. But alkyl shifts, so I've had a few students that have asked this type of stuff. They'll sort of look at alkyl shifts. An alkyl shift is not a resonance form, right? An alkyl shift leads to an entirely different molecule. It's not leading to you know what I mean? It's not an alkyl shift because something can go through the alkyl shift. It doesn't make something more stable. It's just a possibility. And again, alkyl shifts, we're going to see them on occasion, but you'll never be asked, with the exception of a few, to predict an alkyl shift because, again, they can be rather difficult to predict. And unless you get a question, say, for example, that says, here's the product that involves an alkyl shift, you might be able to need it. But there's only going to be about 2 specific examples that actually involve alkyl shifts. So don't get, you guys get all up on the alkyl shift like it's the most important thing in the class. And it's complicated, and I think a lot of you guys spend time trying to study it and understand it, and that's good because it helps you redraw molecules and see the bonds and so forth. But as I said during our review where we spent 70% of the time doing alkyl shifts because that's what you guys were asking, alkyl shifts is not a make or break component of this course. Okay, it's an advanced concept, a little bit more advanced, a little bit more trickier to see. Certainly work at it, but don't put that at the sort of forefront of your total thinking. Okay. All right, so this is Markov-Nikov addition. Point being, think through the mechanism, look at the carbocation intermediate that's more stable. Think of the product that leads from that or that comes from that, and you don't need to memorize anything, right? You can just sort of think about it and rationalize it.
So what was the conclusion of the...
You're going to get a mixture, close to 50-50 mixture. Yes?
But aren't they the same thing? Because if you rotate the bottom one on base, it's going to look like the first one.
No, this one would have an OH and there would just be a CH3 on one side. This one would have been completely symmetric. Sorry, I erased it, but yeah, just draw them out. You'll see. Like one of the if one's like 2 pentanol, the other's 3 pentanol. All right, so now let's get into the predicted mode. Okay, so what I'm going to show you guys now is another reaction that's virtually identical, right, to this one. And what I'm going to ask you guys is let's not even look at the product. Let's just try to think of what might happen. I'm going to take this alkene and I'm going to treat it with HBr. Okay, and the question that I have for you guys is what's the product that I'm going to get out of this? Many of you maybe have read ahead, but for most of you this is the first time that you're seeing this. No idea what the product is. What I'm telling you guys is if you think through the mechanism, you should be able to figure out or at least come up with something that seems reasonable in terms of the product. So we'll go through it step by step. Okay, so think about what the final product might be, but we're going to go through it as a class step by step. Okay, so what do you think is going to be the first step in this reaction?
The pi bond is going to react.
Okay, so the pi bond, these 2 electrons that I've drawn there are going to react, right? We draw that arrow going from the system to the hydrogen, and then what's going to happen?
And the electrons that are attaching the hydrogen to the bromine are going to go to
Beautiful, right? Okay, so this is beautiful, perfect, right? So now the question becomes, as we've already discussed, which side is it going to go to? Which side are the protons going to go to?
the hydrogen side.
They're going to go to the hydrogen side. Why?
It's less stable carbocation.
Because the carbocation will then be on this side, which will be more stable. Correct. What's that?
We shouldn't draw the up.
Yeah, I mean, so there's no problem with drawing the other possibility to help you out. But what's going to happen is, as you're going through more and more, the hope is that you get comfortable with it and you don't even need to. Right? So that's the idea, is when you're practicing more and more and more and more, you get comfortable and it sort of just becomes, repetitive. So drawing out both possibilities at first might be a good way at the beginning to sort of reason things. But in this case, we could draw out the other one, but I already had it on the board, so for the sake of time, we won't draw. But you could, if it helps you, but eventually, hopefully, you'll get comfortable enough about this that you'll just start automatically go into the more stable carbocation. Okay, so now we've got this compound. What's left? What's left over? Br minus, right? Conservation of mass, conservation of charge. Right? Don't ignore that basic general chemistry stuff. So what do you think happens? Yeah. Right? So there you guys go. Y'all knew the reaction. Right? And so what's going to happen, right, is that now we're going to make a bond between the carbon and the bromine. Right? And so we've added HBr across that bond. Again, we've reasoned it. We haven't just tried to memorize this. We've taken a look at it and we've thought about it through the mechanism, and we've been able to not only predict what reaction happens, but we've also been able to predict regioselectivity based upon what we've learned. Yes? Let's draw it. So the question is this. Okay, so the question is, if I react this with HBr, right, what's going to happen? We're going to get to that same intermediate. And I think the question that's being asked, right, is the product that's going to form is going to have stereochemistry to it, right? So the product that's going to form is going to have right? We're going to have right? We're going to have one of those two products, right? And so the question is there going to be any selectivity of one of these versus the other? Right? Do you guys see what's happening here? Right? So I've just basically had the bromine attack, and again, if I attack from this front face, I'm going to get to this one. If I attack from the back face, I'm going to get to the other one. Does there seem to be anything special, more special, about one approach versus the other? No. Right? So this is very much, again, like SN1 chemistry. Right? If you go through an intermediate that's achiral, there's going to be no preference for that nucleophile to attack from one face or another. So certainly if you carried out a reaction where you're generating a stereogenic center, in this type of transformation, absent from something else going on, right? Perhaps, again, I don't want to overcomplicate this, perhaps if there's stereochemistry over here that might affect the overall outcome, then maybe, but in a basic case like this, no, you're going to get a 1-to-1 ratio. Okay? But it should make sense, right? Again, just because we're building off of what we learned in SN1 chemistry. Yes? So the question is, if you have multiple double bonds, how do you know? Let's ask that question, right? So let's think about that. And again, I think the answer is this becomes an issue of complexity, right? So as we move forward, we're at the very beginning of organic chemistry, right? We're just sort of learning the intricacies of it and the very basic premise. But the molecules we're often drawing are very simple. And so the question that Sarah's asking is, if we have a molecule that has multiple double bonds, is there any selectivity? And I think there's no right or wrong answer, but the question would then be, what's the, let's think about a rationale. Let's say we have this molecule, right? Let's pretend that we have this molecule, and we want to react it with acid and water. And the question might become what product would form. This becomes very, very complicated. And in fact, if I ran this reaction, I have no idea. I could imagine several products forming, and I could argue whichever one, in many instances, like we're like, well, hopefully it'll go this, and we run it. And that's why sometimes in like a synthetic organic chemistry class like mine, it might be a 10-step synthesis, and it'll take 2 years to conduct, even though each step is only, because again, we don't know a lot of times, and it's oftentimes unpredictable. But let's try to imagine what we might think might happen here. Right? In this case, let's think about this. Which one of these alkenes, first of all, might you imagine would be more reactive at first? Hopefully I'm not getting too complicated here, but I think it's a good sort of learning opportunity. Let's pretend that let's go through all the possibilities, right? We have 4 possibilities. Let's think about all of those. Okay? Now, the carbon on the left, so that's one possibility, right? That might be the gut intuition right away, right? I want to put that carbocation in the most stable position. And maybe this would be the one that would form, but let's look at some of the others. Okay, here's secondary, right? But what do you notice about this one? Right? It's got a resonance form. Right? It's a primary, so it's not maybe a great resonance form, right? 6A on your exam, right? Right, but it's still a resonance form. Right? That resonance form might not be the greatest thing, but it's still a resonance form, right? So it still helps stabilize it, right? It wouldn't be as good as if, say, we had a methyl group over there to get to a different one, okay? But so again, so these are reacting with the one alkene. Again, then you would go through that, you would add water into it, yes?
And actually, resonance trumps the degree of the carbon.
So the question is degree of carbocation versus resonance. It depends. There's like charts that can compare and contrast. Again, it's oftentimes very difficult to compare diagonally. So like a tertiary carbocation versus a secondary with resonance might depend upon the type of resonance. So, okay, so oftentimes you sort of see an argument and then you have to sort of make your explanation. But let's just finish this up. Let's just all agree that we're not going to, just for the sake of time, we're not going to protonate and put a carbocation at the primary position here. Okay? Right? So hopefully you guys can see that. But the other one will be there. Right? And so if we protonated this one, again, we have resonance forms. And in fact, these resonance forms are even better than this one. Right? So if you were asked to predict which one might be best, which one might you think? Let's draw this resonance form out. Because maybe we can do a prediction. So if this is A, this is B, and this is C. Again, which one of these 3 do you guys think is the most stable? C. But I don't know. Again, I don't know. This might be what you would predict would happen, but sometimes in your chemistry lab, throws at you something different, and you have to sort of make it. But again, just slow it down, look at the mechanisms, and just sort of consider all the variables. So again, for those of you that knew that this was C, or that thought that it would be C, why? You got a tertiary carbocation as one of the resonances, and it also has the resonance form. Right? So, but again, then the question becomes, well, what's the product that I'm going to get? Right? Then the question becomes, well, is the OH going to add in here? Or then is the OH going to add in here? And actually, I think that's something that you guys will discuss next semester in Organic 2. So we got a lot more reactions to learn. But again, I think that was a good question. And again, if you get things like that, if you're thinking about them, just break it down and try to make a prediction. Okay? Okay, so the two chemical reactions we saw so far involved acid chemistry Okay? But alkenes, instead of serving as Bronsted bases, they can also serve as sort of Lewis bases as well, right? So if we have, or as nucleophiles, right? So we sort of saw them react with acids, they can also react with electrophiles, okay? And one of the electrophiles that we'll often see it reacting with is bromine. So that's a very common one. So alkenes will react very quickly with bromine, okay? So let's think about what the structure of bromine is. Let's draw it out. And bromine is a very good electrophile. Why? Because when you react with it, right, you got a Br minus as a sort of leaving group, right? So take this alkene and react it with the bromine just as you would with, say, HBr, right? And let's look at what that will form. Okay? Yes?
BR2 is very stable. So why would it?
It's not very stable.
No,
BR2 is not very stable.
it's
Yeah.
like when it's happening.
It's not, yeah, it's a very good electrophile. You don't want to inhale it. So if BR2 reacts with this, right, what's going to happen, right? Instead of having a proton on one of the carbons, now what are we going to have instead? Br, right? So again, it's just analogous. It's take the HBr and just put an H with the bromine. In this case, it actually becomes easier, right? Because we're going to have a bromine at that position, okay? And now what's going to happen?
Other BRs.
See how easy this is? Right? No, but seriously, like if you understand the mechanisms, a lot of the reactions you learn will just make sense, and you'll be able to predict them, and they won't seem so overwhelming. So let's go ahead and draw that product. Right, and you're going to add bromine across the double bond. Yes? Okay. Okay, so it's not always this easy, right? We always throw something else in there, right? But again, I think it's best to at least think about it like this. Now, one of the things about bromine that's interesting and adding halogens, so again, similar reactivity will happen with Cl2, similar reactivity will happen with I2. Again, I'm not going to go through them all, it's just analogous to this. If you add I2 to the compound, you're going to get iodine across the double bond. If you add Cl2 across it, you're going to get Cl2 across the double bond, okay? But the thing with the fact that you have halogens, there's one thing that's actually a little bit different about these than you would get against, say, HBr, right? And that's the fact of this intermediate right here, okay? What do we know about, what's one of the most unstable things that we see? What, like when we're talking about resonance forms, what's the one thing that we always try to satisfy first? The octet rule, right? So we're always, it's sort of the get-go, we're trying to help that octet rule. Do you guys see any ways in which that compound, we might be able to draw a, I don't know if it's technically would be considered a resonance form, but do you see any ways that we might be able to draw this molecule? I guess it kind of would be a resonance form. It might have a technically different name, but the way that we might use this and have this molecule in a way that might look more stable. So hydride shifts, but the hydride shifts would again lead to another carbocation, right? What do you think?
Create a double bond with BR.
So, what, go in reverse?
Right.
Well, that would just bring you back. That would just be the reverse of this reaction, yeah.
The lone pair, the
There's no lone pairs on a carbocation.
no, you know, BR lone pair
Yes.
attachment sort of weird thing.
No way. Is that what somebody said? No way. Right? And so this is actually a real intermediate. It's called a bromonium intermediate. And a bromonium. Don't worry about the name. The point is that it's a Br with a plus charge on it, and it's a cyclic system. Yes? Quiet. Right. But what did I just say earlier? What's the one thing that we're always trying to help out? Octet, right? Right. So the octet rule is you know, like it's things want those 8 electrons if they can get them. And so in this case, you know, and again, bromine, I don't know the electronegativity of bromine versus carbon, they might be somewhat similar, but like certainly putting a positive charge on bromine might not look that good either, in addition to the ring strain that's generated. Now, there's one thing about that though, in terms of the ring strain question, that actually is a little bit more helpful about bromine. right? What do you guys think the bond length of a carbon-bromine bond is versus, say, a carbon-oxygen bond? Maybe that's a little outside the box there, but what do you guys think? It's longer. Why? Yeah, right? They're further apart from one another. It's a weaker bond, right? And so what effect is that going to have on the ring strain? Yeah, it's not going to have as much ring strain, right? So again, that's a little bit more advanced, but certainly the added bond length helps with that ring strain a little bit. Okay? Okay, yes?
So you're saying that structure is more stable than when it's BR?
Yeah, I mean, these go back and forth, right? But the point is that this is sort of, I guess you could think about it like a resonance form.
No, I'm talking about this, the first one and the second one. The first one will be formed when another BR...
Guys, quiet, please!
When another BR attacked carbon cation and this one...
It'll make sense. Let me continue my thought. Okay, so in these cases that I drew, there's no stereochemical outcome. Really, stereochemistry doesn't really matter here. But there are instances where you can imagine getting two stereoisomers in this process, right? And so in this case, right, you would have a molecule like this, and eventually you would get to the product, and I'll show this in a little bit more detail, but in fact the reaction becomes a little bit more SN2-like, and that bromine, you're still going to get to the Br2, but the point is that there's a stereochemical outcome that I'll explain that comes out of this bromonium. And hopefully it'll sort of make sense. Okay, so I think the easy one to see is oftentimes cyclohexene ring. Okay, so if I'm going to take that cyclohexene, and I'm going to react it with Br2, okay, I'm going to get two possible stereoisomers. Right? Again, ignoring enantiomers, I could either get this one, which would be sort of cis, right? Or I could get this one where the bromines are anti to one another. Okay? And the question then becomes, what I showed you up here can actually help explain the stereochemistry that we see down here. So let me erase this and let's just go through the mechanism and reason it. Okay, so if I did this reaction, let's all think about this together. Okay, I'm going to take this alkene, I'm going to react with the bromine. Okay, and again, I'm just going to, for the sake of the board space, you guys can look at my previous examples. Again, this is all online. I'm just going to go straight to the bromonium intermediate for the sake of time. But again, you could draw that first intermediate that I showed. Okay, we're going to get to that bromonium. Okay, now the Br minus is going to attack. And what's going to be the net result of that? Right? It's sort of backside attackage. It's sort of SN2-like, right? In a way. And the result of that is that when you add across a double bond and you have two possible outcomes with halogens, you get the trans stereochemical outcome. Does that make sense?
Yeah.
So again, I know that I said earlier, oh, it's so easy, right? And I know that there's all these little tidbits that we have. But again, you can sort of rationalize them through the mechanism, right? You can rationalize them through the mechanism. If you get stuck in a situation where you're trying to remember something or you forget something, just break it down, simplify it, think through exactly what's happening. Okay? All right. Yes?
If you didn't do it by making the...
Guy, quiet, please. You're right.
Would you come up with an enantiomers?
You would have diastereomers. This, I think, I'm sort of on the spot here. This, I think, is chiral. So I think there would be another enantiomer as well that we would get. I'm trying to think. I don't have time to think through the RRS, but I think this is chiral. This is not chiral, for sure. But you might get, if it is chiral, you'd get a mixture of those. But these are diastereomers. If it opened, if it did happen to go for whatever reason not through this intermediate, then you would likely get an attack from maybe either face. Now, maybe the bromine would attack one face. I don't want to complicate it a little bit too much at this point. But. Okay? All right, so what is next? All right, let's throw another one that you guys should be able to figure out. Huh? All right, so guys, quiet please. All right, so how many reactions have we learned today so far? One. One reaction. All right, so bromine. Now we're going to run this reaction in the presence of methanol. Ooh, we threw a little kink in there, right? So we're going to add bromine across here. Guess what? It's not going to add Br2 across, right? Otherwise, I probably wouldn't be showing this. It's going to be slightly different. Let's think about what might be happening, right? What's going to be the first thing that's going to happen? So what do you think is the most reactive components in this? The pi bond and the Br2, right? Methanol's, yeah, right? It's certainly, if you have methanol with an alkene, nothing's going to happen, right? We said that earlier, right? You need an acid to sort of initiate that, right? So the first thing that we're going to do we won't worry about the stereochemistry here. Let's worry more about regioselectivity, okay? So if we're going to react this with this, right, we're going to generate the more stable carbocation. And this is important because this is sort of adds to what we sort of learned previously, right? We're going to get to this bromonium intermediate, okay? And this is actually important. I should point this out really quickly. We didn't really say this, right? This might be a little bit complicating. So I've been saying how everything makes so much sense, and this is one of these things that might be a little bit confusing, but I'll try to explain it in a way that might make more sense. And this is a good question to do it in. Okay, what do you guys think is going to be the nucleophile in this case? The lone pairs on the MEOH, right? And again, the reason for this isn't, Br minus is actually a pretty good nucleophile. But the reason why the MEOH usually adds is we're using that as a solvent. So oftentimes when you see something below the arrow, we're talking about the solvent. So that means that we might have 1,000 times as much methanol as we do Br minus, okay? And so what's going to happen is the methanol lone pairs are going to attack. And the question that might complicate this now is now we really don't have a full-fledged carbocation, right? We have some carbocation character, and we'll sort of get to that, but if you were to sort of look at this right off the bat and you were to ask yourselves, which side is that going to attack from, which side might you think? So some of you guys might say, well, it's sort of SN2-like, so maybe it's steric, so maybe I might expect it to go this way. And so I think that would be a reasonable argument, and that's why I'm saying this might be where you have to listen to me and actually trust what I'm saying here. But it actually turns out that in this chemistry, it actually is much more of an electronic argument, okay? And the reason for that is that you have a buildup of, again, we have those two resonance forms. And what that leads to is a very strong buildup. We have two, if we think about what's going on here, we have two resonance forms, right? Right? And so the sort of net result of this, right, is that again, when we're talking about these resonance forms, we're talking about structures like this. The answer, the sort of actual structure isn't any one of these, right? It's sort of some combination of them. But the fact is that this intermediate has a much more character like this one than it does like this one. And so this is oftentimes, we'll write the delta. There's a much more strong delta positive at that carbon. And so it's an electronic argument. That's something I think I was telling some people in my office when they were like, how do I reason things? In chemistry, it's either going to be steric argument or an electronic argument. So it's always going to be some mixture of those. And so what's going to happen is the methanol is going to add to that carbon. So again, you can reason it. Again, this one I think is a little bit maybe not as intuitive, perhaps, as some of the other things that we've seen. But you can reason it. And again, it's not, I don't think it's as clear of a reasoning because I could see many people thinking how it might go the other way through a steric argument, but it turns out that this is an electronic argument. Yes?
Why is that carbon slightly positive one?
because in terms of the mixture of these two, right, it's much more closely related to this one because of the stability of the carbocation. Right, the stability of the partial positive charge here is much greater. Right? So that's why I'm saying this one maybe is not quite as easy to sink in, so you have to sort of grasp it a little bit and sort of take my word for it. Which I don't like to often have you guys do, but in this case, you kind of do a little bit again because there is that other argument. But that's where chemistry, again, as we sort of said, oftentimes in chemistry, there's an unpredictable nature of it, right? And sort of what you get. And we don't necessarily always fully have a beautiful, crystal clear picture of what's going on, but I think we'll try to paint it as at least predictable as possible and as logical as possible. So again, I'm going to deprotonate. I'm not going to show the deprotonation step again because the methanol would add in. We would have that proton on the OH. We showed this previously. I'm not going to show it again, but there would be an intermediate where you'd have the O having a positive charge on it, right? So that hydrogen I sort of took off in that second step. Okay, so for the sake of time, I won't draw that in, but you guys should, because you should draw all your intermediates and make sure that you see it. Okay? So that's, again, technically all these reactions. We've just spent an hour talking about reactions, and it's all the same thing. Yes?
Does fluorine do the same thing too, or no?
Yes. Fluorine?
Fluorine.
No. Fluorine's not as... We don't generally think of fluorine in this reactivity. It might. Do you know about this fluorine reaction? Chlorine, absolutely. Chlorine, absolutely. Fluorine, not so much. At least we don't, if it does, I'm not as familiar with the reactivity of fluorine. FL2, or F2, I'm not too familiar with. It's generally not something we think of. Okay, so again, everything I just showed you guys, 4 reactions that are basically the same. Yes? Quiet, guys. Yes. Absolutely.
So wouldn't that intermediate, that cyclobromine intermediate not be favored as much because of the NaOH can stabilize?
Yeah, I mean, so that's kind of what I was saying before. I'm glad that you're asking these questions, right? So there are these variables, and again, sometimes it's not near as quite as predictable. So could the MEOH stabilize that carbocation and make it feel more like this? Maybe, but oftentimes that's one of the things I think can be difficult about chemistry is, it's still a very young field in terms of understanding all these reactions, and so we can't see. Yeah, we can't open it up. We have spectroscopy techniques that you guys will learn of that'll help us sort of understand to an extent, but oftentimes it's difficult for us to have such a complete picture as to, what's the methanol doing with this? Why wouldn't it necessarily be stabilizing as much? And again, it's probably just a relative energy thing, right? It's probably this plus methanol coordinating isn't as stable as this plus methanol coordinating. What are the reasons behind that? Well, there's a lot going on there, right? So, all right, so anyway, and the point of the matter is that there is probably a certain extent of that helping stabilize it, yes?
So does the Br minus come in and grab the hydrogen that was on MEOH?
You could. Yeah, you could, or you could have the MEOH do it. So the second step could be multiple different things. So I'm trying to sort of, that last deprotonation, draw it out, see it. I showed it earlier. I'm not necessarily going to always show those for the sake of time. Okay, so everything that we've done so far has been virtually the identical mechanism, right? The alkene's reacting with something, and then some nucleophiles coming in and reacting with the sort of carbocation, right? The next couple of reactions that I'm going to show you are not mechanistically related, per se. We would rationalize them through a mechanism, but I think the best thing to do about these reactions is sort of recognize that you can add across an alkene in one way, and we have ways if we want to add across it another way. Okay, and so that'll hopefully make sense as I'm explaining it. Right, so in that chlorine iodide, when I'm saying Br2, I'm sort of referring to both also Cl2 and I2. All right, so in the case of a standard alkene, I'll just write R there, right? If we want to take this molecule and we treat it with acid and water, right? We're going to get the OH there. But what if we don't want that? What if we want to add water across this double bond and we want to change it up? So this is what we might call anti-Markovnikov. So this isn't the one that the standard mechanism would tell us behave. This isn't the product that acid and water would lead to, okay? But the addition of water across the double bond is still a very useful reaction, and so it turns out that some people, Brown and some others, have done work on a way to actually get this reaction to take place in this, what we call anti-Markovnikov fashion. Okay, so this one's going to be a little bit different mechanistically, but it's one that you got to learn. And for whatever reason, this is one that people seem to have no problem remembering. So it's a two-step process. The first thing is going to involve borane. Okay, now there's lots of different types of boranes that can be there. I'm going to simplify many of these just by saying BH3. You know, there's probably 50 different BH something reagents that you could use. Some work better in some substrates, some work better than the others. I'm going to simplify this by just in general, we're going to write BH3 for all of them. Okay? Okay, and then in the second step, so there's a two-step process. The first step is going to be BH3. The second step in the process is going to be you're going to oxidize this with H2O2. And actually this is done in a slight base, so it's H2O2 and sodium hydroxide. And the net result of that is actually NaOOH. So this is the sort of reactive intermediate that this is going to involve. Okay? Okay, so now if we think about this, again, this is a much different reaction, and this is one that might be much more difficult for you guys to predict than, say, acid and water. But I think we can reason it, and in fact we'll be able to reason regioselectivity using what you know, even though boron isn't really something that we see that much, okay? But what do we know about boron? What kind of molecule is boron? It's got an empty p orbital. Well, it's got an empty p orbital, right? It's got an unfilled octet. And so what are boron-containing molecules generally, like that are neutral? What type of molecule? Yeah, they're really good Lewis acids, right? Because they want to accept electrons. Okay. And so if we take this molecule and re-react it with boron, which side is that going to go to? Which side is the borane going to end up on? What's that? Less sterically hindered. Why? Well, let's not do circular arguments here. So the boron's going to end up on this carbon. Let's think about what we've learned. If the boron ends up on this carbon, what's going to be over here? Carbocation, which is more stable, right? Now, formally, it doesn't happen exactly this way, but I think it's good to think about it this way at first. Okay, I think this is a nice way to at least think about it stepwise. As we'll talk about, this is actually concerted, but again, I think at least at the beginning, in terms of rationalizing it, it's good to think about it in a stepwise manner, not too different than what we've seen, right? And so you see how this has all happened here? When we react with the boron becomes negatively charged, right? And this is one of the things, like anytime you guys are thinking about octet rule and how, man, I can't wrap my head around the fact that the octet rule is so important. Think of boron, right? Boron is happiest in a negative charge, even though it's not as electronegative as, say, carbon, nitrogen, or oxygen, right? It's less electronegative than those, but it wants to take on this negative charge because it wants to fulfill its octet. So that's like the thing to think about if you're sort of confused about just how important the octet rule is. Okay? And so now, if I'm going to be at this intermediate, this is a little bit tricky, but what we're going to do here is kind of like a hydride shift, right? It's kind of like a hydride shift. What's going to happen is we're going to deliver, it's not a 1-2 hydride shift, it's more of like a 1-3 hydride shift. But what we're going to do is that boron, again, it has a very negative charge on that. So you can think about that as being sort of like an H minus, right, with 2 electrons. And those are going to go over to that carbocation. Now this is how we can rationalize it, okay? And that will get us to this product. Okay? Now it turns out that this isn't exactly how it happens. There's a certain stereochemical outcome that suggests this is a more concerted process. And when I say concerted, what I mean is that both events are happening simultaneously. Okay? It's more of a concerted process. You can often reason this concerted process, perhaps through a steric argument as well as an electronic. Right? I think it's good to try. I think sterics is easy to think about, so anytime I think you guys can try to explain something from an electronic standpoint, it strengthens you more and makes you smarter. So you can think about that as being sterics, but that's really not that sterically bulky, right? So that's why a lot of times people have bigger groups out here to sort of take advantage of the steric component. But again, the electronic argument leads to that same borane intermediate, okay? And so this is what happens first. This is the first step in a hydroboration, okay? So when you're running one in the lab, you take your borane source and you take your alkene and you mix them together, okay? And then when you're done with that, you let it react for a certain amount of time. You have a whole bunch of this in the reaction vessel, and then you're going to take this and you're going to react it with NaOOH, which is going to be a solution that's going to be made where you're going to take aqueous sodium hydroxide and hydrogen peroxide, and you're going to generate this peroxide. Now this mechanism is a little bit more on the difficult side. I'm going to show it to you guys. This would be a mechanism that would be an icing on the top mechanism. It would be one of the more challenging questions on an exam. But I would suggest that if you're on top of stuff, you know, if you're still struggling to catch up, this is something that I might not worry about too much. But if you really are on top of stuff, it's worth it to think about this mechanism because, again, it will reinforce your knowledge. Now, if you take this molecule, let's think about this from a mechanism standpoint. Let's get rid of that sodium just to sort of get it out of the picture. Okay, if I were to take these two compounds and react them together, what might you think would happen? What do you guys think? Let's think about this. Let's identify what kind of molecule is this? Yeah, it's either going to be a base or it's going to be a nucleophile, right? It's a charged molecule, so it's going to want to give up those. It's going to want to get rid of that charge in some way. Where in this molecule might it want those electrons?
The one on the right is a partial charge. The carbon on the...
It's not attacking a carbon. The boron, right? The boron has an empty octet, right? And so if we can make a bond with that boron, we're going to help out that octet, right? And so the first step in the oxidation step of the hydroboration oxidation is that we're just going to take those electrons and we're going to go, right? That's no different than if it was reacting with, say, a carbocation, right? It's the same type of thing. We don't have to push electrons anywhere else because it's going from something that doesn't have an octet and now it's fulfilling that octet. Okay, I'm going to rotate around this a little bit. Okay, so that should be no problem. You guys should be able to see that no problem. It's this next step that I think is a little bit more complicated. Okay, and that's what's going to happen is we're going to do a rearrangement here. That's again nothing that you guys have seen before. So this when I said that 10%, or so when I said that 90% of the reactions are going to all be the things that you've seen before. This one we can try to reason it, and I'll try to go through it and reason it for you guys. But this is certainly one that sort of will stand alone in terms of mechanism. You're rarely going to see this, but it does have an element of it that's similar to some of the alkyl shifts that we've seen, and so I'll try to explain it from that standpoint at least. Okay, I'm going to just erase this. Actually, I'm going to give myself more board space over here because I need a little bit more space for to see this. Okay, so we've got a boron that has a very strong negative charge on it. We just saw in the previous mechanism, right, that the hydride, right, that because of the fact that this boron had this negative charge on it, the impact of that is that the things that are bonded to it also take a component of that negative charge, right? So you sort of have these guys all become somewhat good nucleophiles in a way, if you think about that way, right? They have this sort of negative charge to them. They're willing to sort of leave with those negative charges and go somewhere else and do some chemistry. And it turns out that in this case, in a hydroboration oxidation, these two electrons that I've shown right here are going to be the ones that are actually going to move. Okay, and you think about that. You can, if you're in a situation where you're trying to think of the reaction, this is for whatever reason, maybe it's the first one of the first reactions we learned. But students tend to remember this reaction. In terms of the mechanism, just remember that there's got to be an oxygen in there. Maybe that can guide you in the right direction. Okay, Now what's going to happen here is that these electrons are actually going to leave that boron. Okay, it's going to make the boron neutral. Okay, it's going to attack this oxygen, right? And the result of that is going to be that we're going to leave OH minus. Very complicated, more complicated than anything you guys have seen before. So if this looks confusing, take it home with you, try to draw it and understand it. But again, if you're struggling understanding basic mechanisms, I wouldn't get held up with this.
Better to maintain the octet rather than neutralize.
Well, watch what's going to happen. Right? So what's going to happen here now? So we're going to have a hydroxide as our leaving group. Now the question was, well, isn't it good to have, doesn't want to have an octet rule? Yeah, but again, chemistry happens, right? That might be high in energy, but eventually it's going to happen. It's the same thing that happened over here, right? The boron had those charges on it, and eventually you go to the lowest thing. This is chemistry. Chemistry happens, you go over high energy barriers, and so things happen, and this wasn't discovered overnight. This was something that took time and one individual's almost entire career to really understand a lot of the chemistry behind boron. You won a Nobel Prize for it, but so I guess it's worth it, right? So, and certainly we've all benefited from it. So now what we have is this intermediate here, okay? And now we can just, usually there's a workup, there's a lot of sodium hydroxide in water, and what's going to happen is we're just going to hydrolyze off that borane, okay? So again, you can think about that as being you can think about this as many different ways. I'll draw it with the hydroxyl there. Right? We can go back to that intermediate if you want to sort of see how it can get that octet, right? And then, many different things can happen here. Water can add in an attack. I'll just draw it, I'll just draw it going from here to here, just as we had seen previously. But again, there's water, and eventually that water is going to go in and stabilize it. Right? So you're going to get to that intermediate plus the borane. And again, this is going to become protonated during the workup. Right, and so the result is that now we've added, instead of adding water across in a Markovnikov fashion, what we've done here is now we've added, again, there's a hydrogen that came from earlier, that's going to be there, and there's the OH. So we've added it across in an anti-Markovnikov fashion. Okay? All right, so we're going to continue alkene chemistry next week. But again, this is just try to relate everything together as much as possible. I don't think we have class Tuesday, so I guess I'll see you guys Thursday.